Okay, well, let's finish up lecture 3 with ore mineral formation and the Goldschmidt rules. So you go, oh, we heard it. Didn't we already do Goldschmidt? Well, that was the Goldschmidt classification. These are the Goldschmidt rules. So Goldschmidt was a very important figure in this kind of stuff. Anyway, I'm not sure what this cartoon has to do with the lecture, but I am a sucker for googly eyes, so um, there you have it. All right, ore deposits are composed of minerals. We already said that. There are thousands of minerals. We already said that. What determines which minerals form at a given time and place, and what determines what metals go into them? Which it's 3 types of rocks: igneous, sedimentary, and metamorphic. What kind are mineral deposits? Well, the answer is none or all. We do describe ore deposits as igneous rock hosted or sedimentary rock hosted, and sometimes metamorphic rock hosted. For example, porphyry copper deposits are igneous hosted, and Mississippi Valley lead zinc deposits are sedimentary rock hosted. And orogenic gold is metamorphic rock hosted, but we implicitly recognize that mineral deposits differ a lot more than the simple threefold classification of rocks that we teach and know so well. So what determines what elements combine to make a mineral? And so the short answer is thermodynamics and kinetics. So thermodynamics is that branch of chemistry that specifies that systems tend towards equilibrium in which the phase, solid, liquid, or gas, with the lowest total energy is favored. And of course, if the solid is favored, then you have a mineral. And if you have a liquid that's favored, then you have a solution. We've covered solutions quite a bit. And then the other thing that determines it is kinetics. So kinetics is never, it's sort of the Rodney Dangerfield of chemistry because everybody is eager to calculate thermodynamic equilibrium, but kinetics really plays a big role because it determines the rates at which systems approach equilibrium. And this is also important for nucleating new minerals. Some minerals, it's hard to nucleate new ones. So when you nucleate one, these minerals tend to grow to very large size. In other cases, it's very easy to nucleate new minerals, in which case you've got lots of very small minerals. So to keep these two things straight in your mind, kinetics dominates at low temperature and thermodynamics dominates at high temperature. So kinetics is not an issue in Earth's mantle because you're down at 1300 degrees or something. But it is an issue on the surface where you've got all kinds of disequilibrium. For example, you've got a granite countertop in your house that is thermodynamically unstable, but the kinetics of it turning into what it should turn into, clay, is so incredibly slow that you don't have to worry about your kitchen counter turning into clay one night. But the point is that kinetics and thermodynamics are two things that determine what elements combine to make minerals. So thermodynamics tells you what minerals should form. So over here on the left, we've got our separate atoms. Maybe they're ions in a solution with a certain EH and pH. And then for some reason, they begin to nucleate and you begin to get a seed crystal. And that once you have that nucleus, then that other ions will be attracted to it. And then eventually you end up with a euhedral crystal, perhaps. So that all of that is being described in terms of Gibbs free energy, whether or not it should happen. It doesn't tell you if it's going to happen, but you do know that at higher temperatures, things tend towards equilibrium. At lower temperatures, they don't. But kinetics is important in this process because it tells you about the rates that new minerals nucleate to make these seed crystals. And it also tells you about the diffusion rates of different elements needed to grow crystals, right? Once you join a crystal, you've depleted the surrounding in those ions. And unless there's a fresh supply of ions, that mineral, that seed will not grow. So that the fluids are very good for bringing in new supplies of ions. So what determines which elements combine to make minerals? So this is a long answer. This is the first of 7 parts. So the combination of elements to form minerals is governed by a combination of physical, chemical, and environmental factors. So there's chemical compatibility, which ion charge and size. There's environmental conditions, temperature, pressure, and water presence or absence. There's the element abundance in the Earth's crust. And then there's the formation processes. Matt covered that, and we can simplify it another way: crystallization from magmas, precipitation from solutions, either low temperature, high temperature, connate, meteoric, all sorts of solutions, metamorphism, and weathering. And then time, these things don't form overnight. And finally, biological influence. Biology can do strange things to concentrations of certain elements. So, chemical compatibility, ionic charge and size. Elements combine to form minerals when their ions have compatible charges and sizes. So, for example, sodium, the little green cation here, and chloride, the yellow cation, they balance charges and they're suitable sizes to form a stable crystal structure. Similarly, calcium carbonate, we have calcium cations bonding with carbonate anions to form either aragonite or calcite. Their sizes and charges are complementary, and it's not hard for them to get together and make a geometric solid, a mineral, right? But there's only certain combinations that will satisfy both the charge and the size. So environmental conditions, that includes temperature, pressure, fluid presence, EH, and pH. So that where and what minerals form is controlled by environmental conditions. So obviously, temperature and pressure is important. Different minerals are stable under specific temperature and pressure ranges. For example, the mineral kyanite, Al2SiO5, one of the 3 polymorphs of the aluminosilicate, it forms under high pressure conditions, while andalusite forms under low pressure conditions, even though they both have the same chemical formula. And pressure is also important in determining whether the magmatic fluids are retained in the system. They generally are under high pressure or released under low pressure. And mineralization can be caused by the release of the fluid as the solution approaches the surface. The water presence. Water facilitates the movement of ions, enhancing the growth of mineral crystals. So hydrothermal fluids are particularly powerful because they are hot, ion and complex rich waters, and so these are particularly important for forming minerals. Now, we've already talked about EH, the measure of the system's oxidation potential. High EH favors oxide, low EH favors sulfides. Some metals are in solution at low EH and precipitate when EH increases. These are oxidation fronts. So uranium deposits in particular form where there's an EH boundary. These are called the roll front deposits in sedimentary rocks. They're very important in South Texas. pH, of course, is a measure of the abundance of hydrogen versus hydroxide ions in aqueous solution. And we've already talked about that. Carbonate minerals can only form in basic solutions. So all of these factors have to be considered or at least you have to be aware of them, even if you can't reconstruct them. So here we've got a phase diagram. And one of the nice things about economic geology, mineralization studies is you don't really worry too much about phase diagrams the way we do in igneous petrology. That we inflict pH diagrams on you instead. But here we're looking at a very simple phase diagram. We're looking at the coexistence of H2O as a solid, a liquid, or a vapor, right? And so we're quite comfortable. Right here we are at the surface of the Earth. We got 760 millimeters of pressure. So if it gets too cold, like 0 degrees centigrade, it'll turn into solid water. And if and most of the time we have liquid water, and of course we can boil it with a higher temperature. Very simple phase diagram. Now, this is a simplified basalt, and we inflict this on our introductory sort of our petrology classes, and we make them understand what happens as you go from a liquid to a, cooling to form new minerals, eutectic, all of these things. This is very, very common, but we're just varying temperature and composition. Very simple system. So its temperature, pressure, and composition are especially important for igneous rocks. And this was the reason that experimental petrology became very well developed. All you have to do is heat different bulk compositions at different pressures in the lab and see what phases form. Very useful way to understand what happens in Earth's mantle to make magmas and crystals. But it's not nearly as useful for studying ore deposits because mineralizing systems depend on so many more variables, right? If you know you've only got 3 variables you have to worry about, temperature, pressure, and composition, phase diagrams are attractive, but how many variables do we really need to worry about in a mineralizing system? I don't know, but it's more than 3. So this is a good example of why mineralizing systems are so much more complicated than igneous rock systems. So here's our good friend, the EH-PH diagram. And I like this one because it's colored so that anything in green is a solid and anything red is in solution. So that's trivalent. That would be in solution only at very low pHs. Whereas iron plus 2 is in solution almost all the way up to neutral. And then depending on whether the EH is low or high, you get pyrite or goethite, which is kind of oxide. But this is EH versus pH. No temperature, pressure, or composition has been introduced here. But it's much more useful for understanding mineral deposits than the classic phase equilibria diagrams. So the third thing is the elemental abundance in the Earth's crust and upper mantle. So in order to concentrate elements, you have to scrounge them from somewhere. So if you don't have any in the crust, it's going to be very difficult for any mineralizing fluid to form the minerals of interest. So oxygen and silicon are the most common abundant elements in Earth's crust. So that leads to the prevalence of silicate minerals like quartz and feldspar. Other abundant elements include aluminum, iron, calcium, and they combine in various ways to make a wide array of minerals, mostly silicates. Now, another way are these formation processes. So minerals form through several processes, as we've discussed: crystallization from magma, precipitation from solutions, metamorphism, and weathering. These are different ways of moving elements around. And then, of course, time. The duration over which a mineral forming process occurs is going to affect crystal size. You look around the geoscience department at UTD, you'll see some monster quartz crystals, and you can imagine how long those took to form. And you might have an estimate, but nobody's going to be able to test you and give you the right answer. But in general, slow cooling allows atoms to arrange into well-formed larger crystals, while rapid cooling doesn't. Forms, smaller, less ordered crystals. And then biological influence. Life processes influence mineral formation. For example, we know some organisms precipitate minerals to form shells and skeletons, and also photosynthetic organisms can form oxidized minerals like hematite. So the formation of minerals is a complex interplay of chemical properties, environmental conditions, element availability, geologic processes, time, even biological activities. And these factors collectively determine which elements combine the diverse array, and when we say diverse, there's over 6,000 of them, array of minerals found on Earth. So when we say it's complicated, we're not just posting on Facebook. All right, so there's two kinds of elements that we can talk about. There's major and trace elements. So we can talk about these this way. Major elements are those listed in the mineral formula. For example, sphalerite, which has got that formula, is 55 weight% zinc, 12 weight% iron, and 33 weight% sulfur. So those would be in that mineral, those would be the major elements. But there's other elements that are found in sphalerite. So for example, copper, which doesn't figure into the formula, can nevertheless substitute, at the level of 0.5%, and manganese at 0.4%, and cadmium at 0.2%. So these other trace elements, in many instances, are more valuable than the major elements. And even when they're not, they still can provide significant additional value to a deposit. So that's how we use major and trace elements in this class. So what controls the abundance of trace elements in a mineral? Well, whether or not the mineral in question accepts the element in question. And what determines that? And that's Goldschmidt's rules. So let's talk about Goldschmidt's rules, not Goldschmidt's classification. And Goldschmidt's rules for element substitution focus on ionic size and charge. So for charge, there's only two rules for element substitution in a mineral. And Goldschmidt's rules about charge are: atomic substitution is controlled by a charge of the ions. It cannot differ by more than 1. So for example, iron +2 can substitute for copper +1, but not iron +3. Okay, for iron, and then for ions of similar radius but different charges, the ion with the higher charge enters the crystal preferentially. So for example, if sodium is the major element, let's say in a feldspar, then calcium +2 can substitute, but not iron +3. Okay. And the other Goldschmidt rule is size. The atomic substitution is controlled by the size, the radii of the ions. So free substitution can happen if the size difference is less than 15%. And we could call that a compatible element because that mineral wants that element. And you can get limited substitution if the size difference is 15 to 30%. And there's really no substitution if it's greater than 30% size difference. And that's an incompatible element. So when we're talking about mineralizing systems, in geology, we'll talk about compatible and incompatible system elements because we're talking about them relative to the mantle. When we're talking about an ore deposit, we're talking about compatible versus incompatible relative to the minerals that we're interested in. Okay, so we can talk about compatible trace elements are those that satisfies Goldschmidt's rules both of them, and incompatible elements are those that don't. So if we think about a solution and it's precipitating a mineral, let's imagine it's sphalerite, zinc iron sulfide. So things like copper can substitute, and maybe it's a compatible element, but things like silicon can't. It can't. So compatible and incompatible refer to the elements of interest and the minerals of interest.
Mhm.
And that is it.